Okay, thank you. So, the Higgs mechanism is known already in 1964, something like that. Peter Higgs and other, and Francis Englert and Robert Brout, some other people. But the Higgs mechanism was applied to the standard model by Stephen Weinberg for the first time. And this paper, a model of leptons, Stephen Weinberg. I think that paper is still readable. At that time, people didn't know whether the same model, the structure, the gauge structure, is still maintained for quarks. But we know that the similar discussion can be applied to quarks. But the basic ingredient of the electroweak symmetric breaking and mass generation is already, you can find that, I think maybe probably 1967, something like that, in this paper, for which the Stephen Weinberg awarded Nobel Prize. I mean, include together with the Glacier, right? Glacier, Weinberg, and Salam, right? At that time, there are several candidates for the standard model gauge symmetry, but experimentally, the Glacier Weinberg Salam model has been was proven to be true. So electroweak sector plus leptons. So leptons, but there are 3 generations of leptons, but the family, the flavor structure will be discussed later. Just to let's take only one generation. So these quantum numbers under the gauge symmetry. So electroweak sector gauge symmetry is the is a structure. So as you know, the one is the SU3 color, 2 stands for SU2, left-handed, and this subscript is stands for hypercharge. And we have Higgs doublet. Higgs also can be written in this composed of 2 complex scalars with the gauge quantum numbers by this one. And for leptons, there is no need for conjugate of Higgs, but in order to give masses to quarks, you also need to take the complex conjugate of the complex so Higgs doublet in this form. But then this is not introducing additional scalar, but the same Higgs doublet, you can take the complex conjugate, and the tau2 is the Pauli matrix. So in this case, the quantum number, gauge quantum number. So SU2 is the still doublet, but the hypercharge is -1/2 instead of +1/2. So this is important for masses for quarks. For leptons, you don't need. So then the Lagrangian you can write down. So as you to gauge sector first, the field strength tensor. And the connected term. The connected term for fermions. In this case, we are using the 4-component notation. So electroweak, so lepton singlet couples to hypercharge only. So this hypercharge with a +1, so -1 charge. And the lepton doublet and of course it couples to hypercharge and also couples to electroweak gauge bosons. This one. So here we omitted identity 2x2 identity matrix. Here hypercharge and also gradient, the derivative. So there's a 1 2x2 matrix. It is omitted implicitly there. And there's also, we have a Pauli matrix, right? And the Higgs kinetic term also this one. So Higgs kinetic term, then you see the convention for the hypercharge coupling. You see the it's opposite sign for Higgs doublet, 1/2. Because of that, you have this one. For SU2, they are all in the same representation. I mean, the lepton doublet and Higgs doublet. And then we also need to add the Higgs potential and the Yugawa interaction for lepton. So Higgs potential so V H delta H. So this the potential Higgs potential is function of H delta H because H delta H is the invariant SU2. Of course, SU2 cross U1 invariant combination. So the lowest order in this combination, lowest 2 will be the quad H delta H and then H delta H square. So the mu square is mass parameter, Higgs mass. It's not really different from physical Higgs mass, but this is the mass parameter, and this is quartic coupling, you know. So the Yugawa interaction for leptons. So because we have only one generation, so it's a simple. Then from the gauge invariance, this is the only choice you can take. This one. So this is the only choice you can take. Of course, in general, this Y is the Yugawa coupling. This could have complex phase, but it is known that you need at least 3 generations to get non-zero CP phase. So you can ignore potential complex phase. So this is your coupling. So there is a general discussion on the independent, the physical CP phases, CP violation basis. So in the case of quarks, also there are some non-zero CP phase in the lepton sector. But this lecture, we are going to discuss mostly on the quark sector for CP violations. So here, then you can identify first you can check the hypercharge, right? Hypercharge, this ER is the hypercharge is the same as electromagnetic charge. So -1, which is -1. So H, you can go back, +1/2, right? So +1/2. And then lepton doublet, -1/2, but the conjugate. So then plus this bar is the +1/2. So if you sum them up, you get 0. So hypercharge invariant. And just the second term is the conjugate. So complex conjugate. This one is complex conjugate. And for this SU1 hypercharge, you can check. And SU2 invariance, you can also check. And so ER is neutral. ER lepton singlet does not change under the SU2. So, but the H and L, they are lepton, they are doublet. So since we take the conjugate here, so let L H means L 대가 gamma 0 H, but this gamma 0 acts on the Dirac spinor indexes, and then this is scalar, right? So just you can interchange. So this combination L 대가 L is the SU2 L invariant. So L 대가, so just from the transformation property. So we are going to discuss more on the gauge transformations, but you can convince yourself that this is the SU2 cross U1 invariant interaction between Higgs and leptons. So this is very simple. So, and then the full gauge transformation is also, let me write down here more explicitly, because we are going to choose certain gauge condition for the later discussion. So ER. So singlet, SU2 singlet, but the ER transforms under the hypercharge. So theta Y is a gauge transformation parameter, depends on space-time, so which is local transformation. And in the case of lepton doublet, with the same gauge transformation parameter, but we need to divide by 2 because the transformation depends on charge assignment. So, and the SU2 transformation require introducing additional transformation parameter. So here there are 3 transformation parameter. So also this transformation parameter is a function of space-time. So this is SU2 transformation. This is hypercharge. And Higgs also transform, but the charge is opposite. to the one for lepton doublet, and SU2 transform. It transformed in the same way under the SU2 as for the lepton doublet. And this is the kind of a metal sector, and the gauge field must transform at the same time by the gradient of the transformation parameter. And here, so as compared to the U1 electromagnetism, QED, so G prime supposed to be E in the case of QED, but we have a gauge coupling associated with hypercharge, so G prime instead of electromagnetic charge. And also, SU2 transformation. So here, just to let me call from this SU2 transformation, let me call U of theta. I mean the exponential SU2 part. Let me call the SU2 part U of theta. Then in terms of U of theta, transformation of the SU2 gauge field written in this way. We have discussed for general non-abelian gauge symmetry, but here we specify the non-abelian gauge symmetry to SU2. So it's just a simple application. Right, so this gauge field. Then you can show that the previously written Lagrangian is a gauge invariant. So this Lagrangian is gauge invariant. As you can see, I don't know if you know, maybe I will. So this is the standard model, the curve for the standard model Lagrangian, as you know, right? So, but it's a bit simplification, and I don't know what is missing, but just collectively written for the all fermions, except that the same Lagrangian. Of course, the this one is not complete because there is no gauge fixing Lagrangian. So we need to introduce gauge fixing parameter. Then the Lagrangian is longer. So now we are going to discuss electroweak symmetry breaking and the unitary gauge. Unitary gauge is in unitary gauge. You can choose any gauge because you have a freedom, degree of freedom to transform. So-called Higgs mechanism. So I didn't have time to discuss Goldstone theorem. So in the case of, I mean, when for the global symmetry, the Goldstone theorem tells you that there are number of massless global symmetry. When global symmetry, in the case of global symmetry, big symmetry is broken down to a small group, and the small group belongs to a bigger group, and then you can count the number of generators in each group. generators or dimension of G, dimension of H. Then you can break this by spontaneous symmetry breaking. Then the number of massless bosons is the same as difference between the number of generators. And this we call this all broken generators. We call broken generators. So this is the number of, this is the number of broken generators. The broken, because we are breaking a big group to small group, and some of the generators in a bigger group do not belong to H. So some of them, those are broken, the broken generators. And we call this massless Goldstone boson is the massless bosons are Goldstone boson, Nambu Goldstone bosons, and these Nambu Goldstone bosons are kind of transformation, parameterizing the vacuum manifold. As you know, as you remember, the Mexican head potential, the vacuum has a degeneracy. You can transform along the valley without cost energy. So that is the vacuum manifold, and the shape of the vacuum manifold called Coset space. So Coset space is G over H, and the number of parameters to describe this kind of internal space is number of broken generators. So number of massless bosons. So this is necessary. Of course, this Goldstone theorem is the vacuum must be Lorentz invariant. So Lorentz invariance is required. Otherwise, this Goldstone theorem does not apply. So in some cases, in condensed matter system, the Goldstone theorem does not apply. So discounting the number of massless bosons is not the same. So because of the massless bosons, those are typically problematic for phenomenology. So we need to eliminate them. So Higgs mechanism tells you so this massless number. So if you promote G to local symmetry, then you need to introduce the gauge field because the H also promoted to local symmetry, and maybe so I'm labeled indices for the gauge field differently. Then in this case, some of the actually this this A are the same A, but you are missing something. So these are massless. We are counting this is massless gauge bosons only, but there are massive gauge bosons which do not belong to the massless gauge bosons for H. So there are massive gauge bosons. So those are, let me call A, U, and these are, I don't know how to call this. Just to, let me ordering in this way. So this dimension H plus 1. Let me order the gauge index in this way. So massless gauge bosons are listed in this way on up to dimension H, and the other supposed to be massless gauge bosons before symmetry breaking, labeled in this way from dimension H plus 1, dimension H plus 2, etc., until dimension G.
So this massive gauge boson appears after symmetry breaking of G. If,
yeah,
right?
so symmetry is broken already from G to H. So because H is smaller than G, you must have broken symmetry. The sum of the massless gauge bosons get massive. Here, the massive gauge bosons, the number of massive gauge bosons are, you see how many of them. So just you can count the indices. So then the dimension, number of massive gauge bosons, this one, right? Just to, this is the full gauge bosons. And you have a dimension. This is the remaining massive gauge bosons. And the difference will be the massive gauge bosons. So you have actually the broken generators, number of broken generators. I think the number of broken generators are the same as in the global symmetry. The difference is that we have gauge bosons. In the case of global symmetry, there is no gauge boson. So massive gauge bosons, we know that there are longitudinal polarization. So there are three, right? Two transverse plus longitudinal. So this longitudinal component, actually, we call Higgs mechanism because the would be Goldstone boson. So we have this amount, right? In global symmetry. But this would be Goldstone bosons are eaten by this massive gauge bosons. So that there are number of massive gauge bosons is the same as number of the would be Goldstone bosons. These are not Goldstone bosons. So when you think about Goldstone bosons in global symmetry, they are physical degree of freedom. But these are otherwise concept. So this symmetry is not local symmetry. This degree of freedom will be physical Goldstone bosons. So these are eaten by massive gauge bosons. So counting, you have the correct counting of the number of degree of freedom. So then you don't have to discuss the Goldstone bosons anymore. Just they are eaten, and the unitary gauge will be in unitary gauge, Goldstone bosons do not appear. We call Goldstone bosons the decoupled, so do not appear. The decoupled, I mean, the Goldstone bosons also carry some masses, depending on the gauge condition. So sometimes they are massless, they appear in the Lagrangian. Sometimes they don't appear because their masses are very large and infinite. Essentially, their mass is infinite, so they don't appear in the Lagrangian. So this is the we call unitary gauge. You don't see Goldstone bosons in the Lagrangian anymore. You only see massive gauge bosons. So I think that this is the general statement. Actually, if you think of breaking of small group, larger group to small group, this discussion would apply. So there is no problem because of this massless Goldstone bosons anymore. So now we discussed electroweak symmetry breaking. So electroweak symmetry breaking depends on the potential, right? Higgs potential. It's a simple form. And the mass parameter, we take the mass parameter mu square to negative. So we look for non-zero vacuum expectation value. So it's a minimum of the potential. So minimum of potential, simply we look for constant value of Higgs, which minimized the potential, Higgs potential. And then as in the simple, I mean the U1 symmetry, local U1, you can find that the Higgs, I mean here we need to be careful about assigning the vacuum expectation value because of this because instead of one complex, there are two complex fields, and the upper entry we have a plus charged scalar field. It's the downstairs we have a neutral. So this plus charged scalar will be eaten by the W boson, so charged electroweak gauge boson. So I mean, in any case, this complex scalar could not get a vacuum expectation value. So you are breaking the charge. So you shouldn't break U1 electromagnetism. So then in the background, actual vacuum expectation value, so this vacuum expectation value. So this V is given by in terms of mass parameter and Higgs quartic coupling, as you remember. It's so simple, right? So, but this is the vacuum, and but in order to describe the physical spectrum, the vacuum, the identification of the vacuum is not enough. So you need to do the perturbation. So Higgs potential, you see, we have this shape. If you take the section, so this so real part of y0, and this orthogonal direction, and the imaginary part, for instance. So here we have this is V, this is Higgs potential. So we are not interested in this more complicated potential, but the non-zero vacuum expectation value is taken only along the neutral component. So And then we have a two direction to go. I mean this way, so this way. So and also we have you can do a perturbation around the vacuum in this neutral component, also charged component. So then the complex scalar. So perturbation you can parameterize in this form. So in this form, here psi and h are 4 real scalar. So this is not the unique choice. So just one of the choices for perturbations. So this psi and h, those are field of, the function of space-time. So these are 4 real scalars. So there are 4 real scalar perturbations, as you remember, neutral and charged component. But in principle, you can choose different parameterization. This is a kind of polar coordinate representation, and you can take like a different parameterization, for example, this one. But in this parameterization, you keep the same number of degree of freedom. Sorry, this is V. Around the vacuum expectation value, small, constant background, you have a perturbation. The degree of freedoms, number of degrees of freedom is the same in both cases. But we choose this one, and the unitary gauge. So we can transform the gauge transformation. So Higgs transform, and by the way, this factor, the P factor, let me call this U inverse psi, and U of psi, we are making SU2 transformation for Higgs. Then we have a U inverse in front of it, and that U inverse is cancelled by this U. So you are left with simple form for the Higgs doublet. And also, when you transform Higgs, you have to transform the other field too. And also you have to transform the gauge field. So lepton doublet also transformed by the same transformation parameter. So you can think of this is to, let's say, psi parameter. It's equivalent to choosing the transformation parameter to psi over 2v. So this is the SU2 transformation. And the SU2 gauge field transform I don't know. Yes. Just to specific transformation for the SU2. This one. And then in this case, the hypercharge and SU2 singlet unchanged. So these are unitary gauge. The form of the Higgs doublet can be chosen in this simple form. And the Goldstone bosons would be Goldstone bosons. So of course here the H is a Higgs boson. And this psi would be Goldstones. So in the standard model, we know that the local symmetry, so G equal to SU2, SU2 cross U1, hypercharge broken down to small group, which is U1 electromagnetism. So the dimension of group is we have a 3 from SU2, 1 from hypercharge. There are 4. The U1, we have dimension of H equal to 1. There is only one generator. Because of that, as you can see, the would-be Goldstone bosons. So number would-be Goldstone bosons equal to dimension G minus dimension H, which is 3. So if this SU2 cross U1 is global symmetry, you have a 3 Goldstone bosons. But we have a gauge field. So because of that, we have a mass list. We started from W now we have a gauge symmetry. This is the gauge symmetry. So we have three of them, three gauge field for SU2 and hypercharge. And those become photon. So one mass list and 3 massive gauge bosons. 3 is the plus minus charge W boson and G boson. So this is mass list, and this is mass list. So these are mass list before electroweak symmetry working. So electroweak symmetry working, we have just the number of degree of freedom is the same before and after. So then you can see that the massive, there are 3. So these are complex. So in the real degree of freedom, there is 2 real degree of freedom. So 1, because of the 3 gauge bosons. So it counts. I mean the number of degree of freedom is the same. The number of massive gauge bosons is the same as the number of would-be Goldstone bosons, just broken generators. So Higgs mechanism is working for the standard model in the sense. So because of that, we choose the gauge conditions such that this unphysical degree of freedom do not appear. So that is the unitary gauge. So if you want to keep this would-be Goldstone boson in the Lagrangian, then we call this arc psi gauge, general arc psi gauge. Because psi, I don't know, this psi, there's also gauge fixing parameter we call psi, but this psi also stand for the Goldstone bosons, so arc psi gauge. So let me go to now physics, the details of the generation of masses and the Weinberg angle. So the current from now on, I'm going to discuss generation. Of masses and the interaction terms. Of course, in interaction terms and also neutral current and charged current interaction. And the next goal is to discuss GIM mechanism and CP violation. So we call this a flavor. And the flavors include the generation of masses, also the structure mixings and CP violation, etc. So GIM mechanism the flavor mixing is crucial for GIM mechanism to work. So we are going to discuss this one. A neutral current and charged current are mostly we are going to discuss neutrino scattering process and beta decay and muon decays. So first, let me discuss generation of masses. Do you have any question?
I forgot.
Do you know Jinyoung's email address? Kim Jinyoung. Maybe you can send a message to her. So if she is missing this lecture, I don't know if she can follow the coming lectures, right? And then also there's another student from Professor Ha's group, so Sun-Hee Shin. So she has never taken my lectures until now. I don't know what is going on. So if you have during the break time, maybe you can send a message, or if you have a phone number, you can talk to Jinyoung. Maybe Jinyoung knows about the other students. So, okay. Some of you, if you know them. Okay, so do you have any question? Okay, then generation of masses. So there are generation masses. You may already familiar with that. First, let me start simple. So I think that if you extend the standard model, including dark matter, I think almost the same story we need to follow. So I think if you are familiar with the standard model, I think that there is no problem for extending the standard model. So I think it is important. So fermion mass, we choose the unitary gauge. So then the Yugawa interaction, we are choosing the gauge transformation. We are making a gauge transformation such that the Higgs doublet takes this simple form. And then Yugawa interaction should be written in terms of the prime quantities, right? In this gauge. So just prime. We have a prime for lepton and doublet, Higgs doublet, and just put the matrix form. So doublet is a neutrino, an electron, right? And then H bar is the square root of 0, H, and right-handed. And the other part is just the Hermitian conjugate. So just this matrix multiplications you have to do, right? So this one and this one, electron only survive. The neutrino does not appear. So even if you have an interaction to neutrino, it looks like there is interaction to neutrinos. In the unitary gauge, there is no interaction to neutrinos. But certainly, I think there is a kind of neutron, whether or not neutrino has interaction to Higgs, it's gauge dependent statement. So at least we can say that in this gauge, there is no interaction to neutrinos. So you can expand it. Then, so just multiply this one, right? And then another. So Hermitian conjugate contains minus YE, V, E. The left and right are interchanged, right? So that's why the same coefficient, but here we have a left-right interchange, and this in 4-component notation, we can write down in terms of this projection operator for right-handed, and this one also projection operator with the left-handed. So because you have to remember that there's a gamma 0, so E, L, E, this is the E 대가 gamma 0, and gamma 0, yeah, right? So because of that, you know that this is the, in terms of projection operator, you can write down in this way, and this is the E, P, L, gamma 0, P, R, E. So in terms of 4-component spinor, E, you can see after interchanging, this becomes this one, and also PR square equal to 1. No, sorry, PR. PR square equal to PR. So because of that, we can write down this LR spinor to this in terms of Dirac spinor. So this E is a Dirac spinor. With a projection operator. So because of that, we have a projection operator PR and PL appearing with the same coefficient. So PR plus PL equal to identity. So because of that, this can be written down. So Yugawa interaction, including the complex conjugation. Is in this a simple form, very simple. And the fermion masses can be identified, electron mass is identified with the coefficient. And this Y is Yugawa interaction. So Yugawa interaction square root 1 over square root 2 times ye, and here from the electron mass, so ye equal to, in terms of electron mass, here, that's because of that. The Yugawa interaction can be written in terms of the electron mass. So if you have a larger masses, then you have a larger coupling to Higgs. So Higgs Yugawa interaction depends on the particle mass because of that. So because in the case of top quark, the top quark is the heaviest particle. You could have strongest interaction between Higgs and top quark. So this discussion can be also applicable for the quark sector. So quark Yugawa coupling, you can introduce in a similar way. First, let me introduce down type quark, because so in the quark sector, so let me first write down the representation. So quark it is more complicated, right? So this way, for the lepton sector, there is no right-handed neutrino, but here we have a right-handed for both up and down. So this is our representation. And then you can construct the most general renormalizable. So renormalizable, because here the renormalizability is required. Otherwise, you can keep adding more terms. So renormalizability, so dimension. So we are constructing dimension of the operator smaller than 4 or equal to 4. So because of this constraint, renormalizability, super renormalizable or renormalizable or relevant and marginal operator. So that constraint, then this is the most general Lagrangian you can think of. So first down. So I think the structure is the same as for the leptons in the case of down type Yugawa coupling. So down type Yugawa coupling. So instead of lepton doublet, quark doublet, and H, and the right-handed down type quark, and the complex conjugation. H. So then YU. So for the up quark, it's a little bit different. So you need to introduce tilde. So this is it. So also in this case, we consider one generation only. So if you have multiple generations, 3 generations, then you need to consider flavor indexes too. So you can check also hypercharge here. So hypercharge. So hypercharge. So minus plus 1/6. So minus conjugation minus 1/6. So Higgs was, what was the Higgs hypercharge?
Plus minus half.
Plus minus plus 1/2. Plus 1/2, right? So plus 1/2 and down minus. So if you sum up those charges, they are sum up to 0. So similarly, hypercharge, and this one -6, 1/6 is, and this H tilde I just said opposite hypercharge, and UR hypercharge is here, plus the sum up to 0. So these are up to 0. And for SU2, just the lepton doublet, right? It's the quark doublet. It's the same as for the lepton doublet. So the doublet SU2 transformation is okay. But in the case of quark, we need to check the color invariance. The color invariance, the Higgs doublet doesn't carry color, right? And then this Q bar, Q is a 3, but if you take the conjugate, then 3 bar for Q bar, and UDR is 3. So 3 bar 3 is the SU3 invariant. So this is also okay. So complex conjugate. So then just you can follow the same discussion. Of course, now in the unitary gauge, you need to put prime quantity here in the doublet. This way, and just expand them. So similarly, you will find that quark this one, okay? So because of that, the up-type quark depends on Yuga coupling, and down-type quark depends on another Yuga coupling. So we don't know of course we can accommodate non-zero masses for quarks, but we don't know, we cannot explain the quark masses, why the quark masses are so small, for instance, for first 2 generations, for instance. Just we parameterized the quark masses by the Yuga couplings. Let's make a short break, and then we can continue to discuss the gauge boson masses. Gauge boson masses. And then neutral current and charged current interaction. I think that for today, I think almost all the interactions we can cover. I don't know about the CKM matrix, but let's try. Okay, so important, of course, for the standard model, but also for the extended model with the new gauge symmetries. So it will be a good exercise for you. So again, in unitary gauge, we are working in unitary gauge. So this unitary gauge is, of course, I choose particular form of the Higgs doublet in this polar coordinate. You can choose this Cartesian coordinate for Higgs, and then for the general gauge, no, not unitary gauge, general gauge. So general gauge depends on this psi1, this gauge fixing parameter, And then you will see the gauge boson masses depends on this psi 1. I think this has to do with this second term in the gauge fixing parameter. So if we expand that, you have a psi square. Those corresponds to masses for the Goldstone bosons. You can say that the Goldstone bosons are massless, but here there is a gauge fixing parameter which tells you that the Goldstone bosons are massive, which depends on the gauge boson masses depends on psi 1 parameter. So from there, after expanding the psi 1, psi. Sorry for the same notation for gauge fixing parameter and Goldstone bosons. So because of this psi 1, so the Goldstone masses are proportional to psi 1. So then if you take psi 1 to infinity, then you are going to the unitary gauge. So then Goldstone bosons are decoupled. Then that corresponds to setting this psi equal to 0 from the beginning. That's precise. And you can, if you don't like the polar coordinate representation, you can choose this Cartesian coordinate, and then you can introduce the gauge fixing parameter appropriately. Then you can cancel the mixing for Goldstone boson, and at the expense of eliminating the mixing, you are introducing the masses for Goldstone bosons, and the Goldstone boson can be infinite. Then you can eliminate all this heavy degree of freedom. Then you are going to the unitary gauge. So it's a basis independent. So it is the gauge fixing condition that tells you whether the Goldstone bosons are kept or not. But there is the independent. Even if you don't keep the Goldstone bosons, you need to consider Goldstone interactions too. And the Feynman diagrams are more complicated. So, but there is also issue with the unitary gauge. So, okay, it's an interesting issue in gravity. So gauge boson masses comes from the covariant derivative term. So Higgs Lagrangian contains covariant derivative and unitary gauge H prime, and this so double boson primed, right, in the unitary gauge because we transform the gauge transformation. So, sorry. But let me drop the prime just for the convenience. This prime gauge boson contains longitudinal component, so it is different from the unprimed gauge field. But for just convenience, let me drop it. Drop the prime. And H prime is now between this form. And then if you expand that, because this Higgs field is real, so this quadratic term gets simpler. It's a simple form. So just the derivative, when derivative act on the Higgs field, you have only kinetic term for Higgs boson and we have a square and 1/2 factor. Here we have a 1/2 factor, another 1/2 factor from after square. We have a 1/8 in front of it, and this is the matrix multiplication. So the H mu D H, right? So this conjugate. So this and then also other things also take the conjugate, and also round mu H prime. So in this way, right? So because this so absolute scale means in matrix multiplication in this form. So because of that, you need to consider write down the extra term in this form, and this G tau I and G prime P mu tau J. Let me introduce only another summation index for SU2 times. So only these two. And then the second term contains everything for the gauge bosons. So if you have one more Higgs doublet, you need to do the similar calculation. Then you will change electroweak gauge boson masses if you have an extra scala, extra Higgs doublet. Let me expand the SU2 part. SU2 part is written in this form, right? Tau 2, tau 3. So it's the Pauli matrix is this right? So the first two, 0, and this just changing contributing to the diagonal component W. And then here the off-diagonal component, the sum of the real gauge field, we call this plus charged W boson, and the other off-diagonal component is the minus negatively charged W boson. So we are able to write down the SU2 part in this 2x2 matrix form, and G prime, the hypercharge part. As I said, there is an identity, 2x2 identity. So just G prime, because the hypercharge down, up and down. I mean, this in the doublet, you have the same hypercharge for up and down. So you can write down this in this matrix form. Just the sum of them. Then just the sum. So we have a gauge coupling, sorry, G. SU2 gauge coupling in front of it. So in this simple form, so matrix form. So because of that, this the star term, second term can be written explicitly. So zeta term, sorry, this is star term. So one ace. And the scalar of this, a scalar of this one. Instead of taking the square, we know that we have same term appearing twice, but here this one will be multiplied to this one, right? In this here. So I don't want to do this square. Instead, I do this one, and this is just conjugate the transpose, right? This is a transpose. This is, let's say, this is the side, and this is the side. So then this is psi. And the psi, this one is psi. So psi is the two. But by the way, this actually maybe you can write down this one. Let me call this psi 1/8 VH square and psi okay. So psi does not contain this V plus H. So because it will be factorized as an overall factor. Okay, 0.1 for the column vector. So so then after matrix multiplication, you see you have this one. Probably is that there should be complex conjugation. Yeah, sorry, this is not the real. This is not, where is this? This is not the real matrix because this we have a plus and minus. So it is different, different one, sorry. So psi, yeah, we have to, yeah, this is not exactly this one, but I don't know how to call it. I don't know how to call this. It's not the same one, sorry. In any case, if you multiply, there's another combination, another term, another factor with this combination, multiply by 0.1, right? So for that, and just to No. Yes. Okay. So then star. So this product of this and this one. Yes. So, yes. So you have several terms appearing. Here, the second term, you have a mixing. Yes, mixing. Because B mu, W mu, W3 mu, they are mixing. So we need to diagonalize this neutral gauge boson. In order to do that, we introduce Weinberg angle. So these are mass terms. When you ignore the Higgs boson, this corresponds to mass term for neutral gauge bosons. So this should be diagonalized, and you have a G boson mass after diagonalizing. So because of that, this combination must be G. G boson must be proportional to in this particular combination. And there must be orthogonal to that. The orthogonal combination must be photon. Orthogonal combination must be something like this. And then you need to normalize if it is orthogonal transformation. Appropriately, you need to normalize this transformation. That's how you obtain the Weinberg angle. So Weinberg angle, the standard notation, there's some sign difference, up to sign difference, but it doesn't matter much. So the photon and hypercharge and the neutral component of the electroweak gauge boson. Okay, so this is cosine. This one. And here you see the G boson contains here B minus W, something like that. So you can identify the Weinberg angle normalized. This one. And then cosine, oops. G. This way. So I think in this way, I think I think Weinberg angle kind of mixture kind of determines the mixture of neutral gauge bosons. And if Weinberg angle equal to 0, then Weinberg angle equal to 0, then the photon is just given by would be given by this hypercharge only, and G boson would be given by neutral component of the SU2 gauge bosons. But in nature, this Weinberg angle is different from zero. So, and then it has been measured precisely. So because of that, G prime B mu this combination appearing in the mass term can be written down in this form. Only the G boson. And the photon doesn't appear. Because of that, maybe there's some, I forgot something. Is there any, I forgot gauge coupling here, G. Yeah, here we need to multiply gauge coupling here, G. Also here, G. G. Okay. And here, G prime. Okay. So we have fully diagonalized the electroweak gauge boson. And this is the, then we can rewrite the Lagrangian in this form. This way. So the coefficient is identified with the gauge boson masses. So W boson masses square equal to this one, because this is complex field, and G boson mass is also this way. And the photon mass equal to the photon is massless. So we can explain the difference between weak force and this is the electromagnetic force. So long range. And it's the short range. Before that, all the gauge boson masses are all the gauge bosons are massless, but some of them get massive. The photon is massless. And also after expanding this Higgs interaction, Higgs term, you will see that there is a Higgs interaction to WG with a single Higgs, and also we have a quadratic Higgs coupling to W boson and G boson. So from this one, the Higgs can decrease to WW. It is that. And the important thing is that the Higgs appears in this particular form. So in general, you can parameterize this like 1 plus 2a 2b plus b. Sorry. The standard model, you can compare whether this is the standard model Higgs or not. If A equal to B equal to 1, then this is the standard model. But if different from that, then it is not the standard model. And also, so this is Higgs measurement and also unitarity. Unitarity, it is important to satisfy this condition. Unitarity. Maybe this is not quantum FFT course, so I don't know if, so you can just let me mention it. And also Higgs interaction, Higgs potential, you can also identify H cube, H40 interactions too. So maybe just let me skip over to different discussion, because this is not that difficult to identify. So neutral current and charged current interactions. So first, the neutral current. Neutral current interaction, let me focus on leptons, and that can be easily generalized to the case of quarks. So we have from the covariant derivative, we have covariant derivative of the spinors, we have this interaction to gauge field. For the lepton singlet and also lepton doublet. I think just we can keep track of all the interaction term. All right, then so this contains both this term contains both neutral and charged gauge bosons. So in this, I think that if you remember this one, what was the
W3
W3
W1 minus I W2.
What's plus?
If there is square root 2.
Square root 2, okay. And minus 3. Okay, this one. And for neutral current, we keep only the diagonal component. Okay, so the neutral component, we keep this hypercharge as well as neutral component of the SU2 gauge bosons. So neutral current, therefore, we keep interaction only. So interaction is to expand the second term to get the first term, and the second term just to replace this by lepton doublet, also this one. and just expand that. Then hypercharge is the coupled to neutrino and electron in the same way. And W3 part plus G. So then you can rewrite everything, collect terms. I think the rearrange it. Minus. So we have from this second term, we also have left-handed minus. Right, this one. So this electron part. So we have electron part here. Okay, so I don't know where was the there was some, yeah, okay. So the lepton is up is the downstairs, so minus the sign changes. So this one plus G W, okay, and minus and neutrino. We have a neutrino, also another neutrino. So in this case minus. Okay, this is minus. I think this is everything. So then yeah, then I think the in this combination, this is the proportional to the neutral G boson. The neutrino does not couple to photon, but this second term contains both photon and neutral G boson. And also this hypercharge also contains is linear combination. So we need to expand them and then carefully following the details. I mean, we need to take into account the Weinberg angles. Then in the end, you can write down explicitly. It is nice to see that photon does not distinguish chiralities. The photon couples to left-handed and right-handed in the same way. And plus G. And electron couples to G boson. electron couples to G boson, but you see the coefficient are different. So left-handed and right-handed. So G boson distinguish the chiralities. And neutrino couples to G boson only. So in this, then I think the G prime, of course, the Weinberg angle. Weinberg angle is the measurable quantity, but G prime is not directly measured. G prime, we need to change it to physical parameters. So because of that, electromagnetic charge is G prime CW. The CW is the shortened notation, cosine theta W. Also sine W is the sine theta W. So then you can write explicitly G prime times CW this way. Then this is nothing but G times sine W. So you can either obtain electromagnetic charge from G prime coupling or SU2 coupling because of this sign, Weinberg angle. So this is the electromagnetic charge. Now this is the observably measurable quantity. And then you can also massage the other terms, then eventually neutral current turns out to be minus E. I'm writing this in a more convenient notation. So this neutral current, actually this electromagnetic, the first term is the electromagnetic. The other three is the neutral. We call this is neutral current actually, but the electromagnetic interaction also neutral in the sense that the mediator does not carry electromagnetic charge. So, but the electromagnetic. Then you can write down this in a more general form. So this F run for the standard model, or the standard model fermions. The interaction term depends on this tau and electromagnetic charge. So the electromagnetic charge for electron, as you can see here, -1, right? So maybe I need to put E. Oops. So, or it can be written in this form. So electromagnetic current in terms of the current plus neutral current and this neutral current can be written as the third component of SU2 current and the electromagnetic current. So this is a simple form of the neutral current interaction in terms of the current. And here tau 3 is the Pauli matrix, 1 with the 1 minus 1 in the diagonal entries. So tau 3 is non-zero only if F is doublet, SU2 doublet. If F is a singlet, tau 3 equal to 0. So if F equal to tau. Okay, so lepton doublet, neutrino. So for neutrino plus 1, for electron minus 1, in this way. Then you can accommodate all the, not only leptons, but also quarks. So all F can be lepton or quarks or leptons. I think that there are several, I think that this is more, you need to count what is the, where, I mean, what is the value of tau 3 and charge, etc., etc. But you can find also this neutral current, this form can be written, so just J mu. Sometimes we are using this notation. Yeah. So this F, this vector, vectorial, and this is the axial coupling, axial. And then in this case, F is the so Dirac spinor. You can see the tables. So what is the, can take a look, what is this value? For neutrino, electron, and up and down. For charged current, it is so simple, the charged current. So let me go back to this one. So charged current here. Charged current. The charged current interaction.
Why you notated LNC, not LCC?
Oh, okay, sorry. And this component, so this 0 character 2 W plus minus. So again, you expand Okay, right. So here, therefore, so just to expand them to get, so this neutrino couples to electron through W boson. The neutrino plus electron couples to neutrino through the W boson. So this charged current, we call this, we can think of this also coupling to the current. So because of that, I think all the electroweak interactions for matter can be written in this simple form. Sorry, this one. I think that this notation is more convenient. Okay, this one. And also, of course, here charge current contains leptons only, but for quarks, you only have to replace upper or lower entry by quarks. So in the case of quarks, okay, we have a quark doublet is ULDL, right? So just this interaction. So neutrino is up, the electron is down quark, something like that. This one, right? So this current interaction, this current, in particular, this neutral current and charged current. So neutral current, charged current interaction. For charged current, I think this charged current, as you can see, is the two neutrino. So this is a charged current interaction, and so this so here there's some projection operator, right? PL. Also this a PL. So So because of this is a V, the vector, and this is a axial vector. So this charge current, as far as the charge current is concerned, V minus A structure is also at the level of quarks is the V minus A structure. So V minus A structure is very important for the electroweak interaction. For neutral current, on the other hand, neutral current, as you can see, this is V minus A, but if only if V and A are equal, this is a V minus A. But the V, this coefficient, maybe I can tell you, maybe only for neutrinos, okay? So that quarks is more complicated, so neutrino. The V, so neutrino, 1/2. So in the case of neutrino, neutral current also V minus A structure. For electron, on the other hand, this is this one, and maybe we can this one and then okay. This is almost V minus A, but this is not exactly V minus A because of this Weinberg angle contribution. This Weinberg angle, as I said, is measurable, and the Weinberg angle, the third table scale in the G boson mass scale is 0.231. So it is a small value, small number, but it is non-zero. So V minus A is not precise for electron interaction. For neutrino, you can find almost for neutrino is V minus A. So same is true for quarks. The quarks U and D is not V minus A because of this. So for all the charged particles, it is the same is true. For neutrinos, it doesn't carry electromagnetic charge. So it couples to G boson only. So it can respect the V minus A structure. So for the for the rest unit, and I will talk about the connection to the Fermi interaction. And so in the charge current, the Fermi interaction, there are two processes: neutral or charged current interaction. So in general, where is this one? This is. So here, this G boson and W boson, they are massive, so short range. So we can integrate out G boson or W boson to get effective interaction for quarks or leptons. So you can enter. So maybe there are several ways to see how to get the effective interaction. The Fermi interactions for the neutral current, J mu, neutral current, J neutral current mu. So these are four Fermi interaction. So neutral current, in the case of where is the neutral current? This where is the so this neutron current, right? The neutral current is the F mu VF here. Looks like that. And this just a square. Okay. So neutral current induced effective interaction. So this is the effective interaction. If you don't see WG boson directly, charge current interaction is this one. So this the charge current, where is the charge current here? So
what if the fine for the J mu CC, the left one?
Sorry?
I meant for CC,
Mm.
one J contain plus, but the other J does not contain any fine too. I am wondering if that minus or plus.
Which one? I don't know. This one?
The most bottom one, I mean.
This one?
Yeah, the upper side of that.
This
The
one?
Yeah, the left one looks like there is no charge.
Charge.
I'm sorry. I thought the plus look
This is conjugate.
conjugate. Okay.
This is the charging current has a carry certain charge, right? Because it couples to W boson, and a combination of this combination must be neutral, charge neutral. So I think the charged current is complex because of okay. Okay. So in both cases, this four-Fermi interaction, like this form. I don't know how to say. This structure, the four-Fermi interaction, and some structure there. So gamma matrices in this structure. So in the low energy, you can get all the important interactions between leptons, or between quarks, or between lepton and quarks. So this is the lepton current, and this is the hadronic current. But the hadronic current actually we are measuring the hadronic current at the hadron level, not in the quark level. So in the low energy, this will be replaced by the hadronic current in terms of proton and neutron. So this is the hadron. But just below the electroweak scale, we can describe them in terms of the quarks and leptons. If you go to like a proton scale, then you need to consider proton and neutron instead of quarks. So that's the only need to. So this is the effective interaction, right? This is the neutral current and charge current. Then we can easily identify the coefficient of the charge current and neutral current for muon decay. Or beta decay, the Fermi introduced effective interaction with the G Fermi constant. So here muon decay, muon goes to electron plus the electron neutrino, muon neutrino. So from this effective interaction, you can describe the muon decay in terms of this point interaction. So this point interaction, muon. So muon annihilate to create neutrino, muon neutrino. Then, but these are all at the same point, occurring in the same point in space-time, right? So point interaction. So the electron, the anti-electron. But we know that this can be expanded in this form by including the charged gauge boson. So at the level of amplitude, you can, the decay amplitude, mu to E. So this decay amplitude, by using the Feynman rule, for the charge current, so we have a charge current interaction. So from the Feynman rule, you can easily identify. So when this W boson carry certain momentum Q square, so this one, because today lecture we have only students from our group, so just I can tell you directly the amplitude. Otherwise, I cannot tell. So here, the momentum of W boson is much smaller than W boson mass. Then you can ignore this momentum in the W boson propagator. And you have a four-Fermi interaction. And this decay amplitude can be written as, so this, from the Feynman rule, you see, Feynman rule for decay amplitude is just from the interaction times I. So from that, I see some sign difference. So the standard notation, I think that this one was minus sign here. So there's minus sign. Also, so this one, effective interaction you can identify from the amplitude, and then this becomes minus G for me over square root U in G for me in the original form in written in this V minus A structure. So instead of projection operator. So from there you can easily identify. So we have a one half factor here from the projection operator. So G for me, effective interaction to describe the muon decay or the beta decay can be identified with the fundamental parameters in this theory. And the G for me is also equal to electroweak scale. G for me. So it's useful to remember this relation. And there's an alternative way to obtain the same effective interaction by integrating out. So you can ignore the connected term for W boson. Then the W boson mass written down here, and charge current and the complex conjugation. So from there, integrating out means you take the you consider the equation motion for W boson without connected term, and you will get some equation motion for W boson. So just you vary the Lagrangian with respect to the plus negative, positive charged W boson, and you can get this equation. Therefore, W boson equal to minus G over charged current. So you can solve this equation for W boson and put it back to the original Lagrangian. Then in the effective Lagrangian you obtain. So W boson here we have a square. So G, yeah. W boson J mu. Then there are same terms with the negative sign. So because of this minus sign here, when you put it back, this second and third term, you have a minus negative contribution. So you end up with this. Okay, so then the charged current is the contains square root of something, and then you write this. Then you will get exactly the same interaction Lagrangian as we derived from the diagram, Feynman diagram, decay amplitude. So this is the way to obtain the effective Lagrangian or effective Hamiltonian. And I think the B meson decay, for instance, recently people discussed about B meson decays. Also, we are using this kind of trick, and also new physics. When the new particle mediator particle is very heavy, you integrating to get the effective interaction. It's useful to remember. Okay, so next week we are going to discuss do you have any question?
So integrating out means the pills are for massive, so they are almost not fluctuate. Is that right?
Yes. You're right, yes. So here almost the W because we are ignoring the connected term. So W boson is the kind of non-dynamical degree of freedom. So you can think of auxiliary field. And if you have some field, auxiliary field in the Lagrangian, you can use the equation motion for that. And we call integrate out at the classical level. So I think the Adriana Jason are familiar with this integrating out procedure in the four-form paper. In the case of four-form flux models, the antisymmetric tensor field is non-dynamical. So we integrate it out to get the effective interaction. So same is true here. And if you have a kinetic term, then if you want to include a kinetic term for W boson, then I think maybe you can treat the kinetic term for W boson as perturbation. So then in the effective interaction here with this charged current only, you don't have derivative term or only field. But if you include the kinetic term for W boson, then you have non-zero derivatives. So I think also at the level of this amplitude, you can expand this 1 over Q square MW. This factor can be expanded in this form. And just here, we are keeping the leading term in this derivative expansion, right? So we took only leading term in order to identify the Fermi interaction, but here we have a higher order momentum dependent term. So that corresponds to including the kinetic term for W boson at the level of Lagrangian. So this is a very well-known procedure. Okay, so next week, if you learn the history in more detail, history of particle physics, in standard model is very, very interesting. And the way to construct the detailed structure is also interesting. You didn't know it from the beginning, but they wanted to explain some experimental data, and they figure out some existence of new particle. So I think it's interesting. I think for instance, when people didn't know about the existence of strange quark or charm quark, the people knew that this structure from the muon decay, and we know that up and down quark, those exist from proton or neutron. So neutron, proton, the neutron decay, for instance, beta decays can be described by electroweak interactions. Then here we had to add additional quarks. At the time, we didn't know about tau, but there is an important implication for the existence of extra quark doubling. So, which was due to the decay mode of K-ion. So we need extra generation. And also we need one more generation for quarks. So in this case, top and bottom, because of CP violation. So if you don't have extra generation, you don't have CP violation. So this is only true when you have 3 generation. Oops. And also, I think that this is the first the K-ion decay. So we had to introduce Kabibo angle. So flavor mixing is very important in the history of particle physics. And also the GIM mechanism also the Kabibo angle has to do with the mixing between down and strange. So this is a mixing between down and strange. And the existence of charm quark, of course, due to the SU2 structure, but this one is also predicted from the K-ion decay, the smallness of decay of neutral K-ion. This decay rate is very small. So at the time, people thought that it's unnatural, and that has to do with the existence of charm quark, predict existence of charm quark, and it is called the GIM mechanism to cancel the leading contribution by introducing additional particle, charm quark. So it's similar to the hierarchy problem. So if you have a large correction to the Higgs mass due to top quark, and you have extra contribution from spore particle, star. And then these two contribute to the same quantity to make the Higgs mass small. So this is I think a very similar situation, and I think the many famous people quote this interesting mechanism. So when they wanted to motivate for BSM physics. So, okay, so the GIM mechanism and then CP violation. So next week, we are going to CP violation has to do with the CKM matrix. And just to, I think the Kabibo, C is the Kabibo, Kobayashi, Masukawa. So Kobayashi and Masukawa, they awarded a Nobel Prize in 2008. And together with the Nambu, but Kabibo passed away before the Nobel Prize. So just Kobayashi, Masukawa. I don't know. Probably Kabibo still still active, but maybe Nobel Committee did missed Kabibo at that time and replaced him by Nambu. But there was I don't know. Sometimes people missed Nobel Prize, they passed away immediately because they are waiting for the Nobel Prize for a long time, and they are if they are not awarded Nobel Prize, they are frustrated, disappointed, and passed away. Yeah, in that case. And also, I think that there's some interesting for the other guys, the other two students. I mean, neutrino scattering is also interesting in the low energy processes. And for us, for dark matter study, neutrino scattering is very similar to dark matter scattering, except the neutrinos are almost massless. But so we have to think about similar processes also for dark matter detection. So neutrino scattering will be also discussed after this GIM mechanism, etc. So neutrino. And also this is a very, I think, the hot topic recent years: neutrino electron, neutrino nucleus scattering, and there's a coherent neutrino scattering has been observed for the first time. It's like a dark matter coherent scattering. So although neutrino or dark matter scatter with the quarks or nucleons, but this the nucleus is composed of many nucleons. The nucleus move as if it is hit. I mean, the coherent is moving, and nucleons, scattering with the nucleons is the origin of scattering, but the nucleus move at once. So these are coherent scattering. So also similar phenomena, but for dark matter we haven't found any evidence for coherent scattering. But in neutrino case, there was evidence the coherent scattering recent years. So it will be interesting, and maybe the experimental data has been improved a lot. But I have to update this. I have a note in 2014. I have to see what are the current update on the experimental data. So it will be. Then after that, I don't know. So the Feynman rules and maybe basic, quick summary of QFT and application to the electroweak processes. Then dark matter will be started in the second part of the semester. Okay. So this is the end of the lecture.